Okay, let's start. Okay, my name is Matthias Kerschhaggl. I'm from EVK in Austria, small, medium-sized company near Graz, and I'd like to talk about quantitative chemical imaging today, as we use it in the production line. Probably not known technology to everybody of you. So the contents of my talk would be a short company presentation, okay, followed by two applications, specific applications where we use this novel technology for production processes, and then I will conclude with like a summary or outlook and a vision that I see for hyperspectral imaging, chemical imaging that can be used. So EVK is an expert company in the area of industrial imaging, and we are using our proprietary hardware, which is based on technologies like, as I said, hyperspectral imaging, but also conductivity imaging, which means metal detection, as well as RGB cameras. And over the years, we gathered more and more expertise in using those technologies in production lines, combined it with software that we wrote ourselves and algorithms. And so we developed into the field of being solution providers. At the end of the day, nobody just buys a camera unless he or she is an expert. It's more that people are buying solutions to their problems. So our core expertise, as I said, is set mainly in the field of these three core technologies. And at the end of the day, we are going to the line and deploy these technologies and bring benefit to the customer. So our solutions mainly consist of sensor heads, let's say data acquisition systems, where we gather raw data. Can be RGB data, can be a phase amplitude diagram from a metal detector, can be hyperspectral data. Whatever it is, we apply algorithms to it, some data intelligence, to harness this data and infer the interesting information that can be used to arrive at a, let's call it, business decision. A business decision could be the sorting of a good from a bad product in a product stream. So that's why we evolved into the field of sensor-based sorting, where you can use these sensors in sorting machines, for instance. All the applications we are designing are set in the industry. We sell a little bit also to universities and laboratories, but the main markets are industrial applications. So the company history started in the late 80s, where the company started off with projects dealing with microcontroller systems. They were new at the time. But over the years, products arose and were developed, and we actually were the first company in 2006 to deploy hyperspectral imagery in the sensor-based sorting environment using an embedded smart camera. And nowadays, we are writing more and more software because these high-dimensional data are quite complex to be analyzed, and there's a lot of hardware on the market now, but there's not enough expertise out there to use this data. So we concentrated more and more on delivering applications and the necessary tools to use these cameras. Our solutions are you can find them, I mean, after 30 years, all over the world. Of course, with a cluster in Europe, since Germany, Italy, France, and so forth are important countries where you will find machine builders, but also in North America and in more evolved countries in Asia. So the core markets, after starting in the field of recycling more or less, are nowadays the food segment, because it's an ever-growing market where more and more optical sensor systems and data acquisition is needed to guarantee for the quality you are expecting in food commodities. So what you can do with hyperspectral chemical imaging there is basically foreign body removal from a product stream, like imaging French fry production, where you can find bones or even golf balls, stones from the field. When the farmer is delivering the tubers, you will find all sort of stuff you do not want to find on your plate. So you can remove those foreign bodies using hyperspectral chemical imaging, but you can do more than that. You can also infer concentration measurements or concentration information from foods or chemical ingredients, like, let's say, sugar content, protein content, moisture, fat, you name it. And that's very helpful in the production to shape your product and to make it perfectly fit to the requirements of the end customer. A smaller market, but very interesting, a market that has to be evolved is the pharmaceutical market. It's a very strictly controlled, highly regulated market, but it is in need of new technologies, because also pharma is changing, because their blockbuster products are not at hand any longer, so they have to invest more and more money to also get out the best of their production lines. Here you could imagine inferring the active pharmaceutical ingredients concentration from, say, a tablet or a pharmaceutical powder or any other product. This is possible using chemical imaging, for instance. An old but good market is the recycling industry, there where it's all started, because hyperspectral imaging, if you use it in the near-infrared regime, basically gives you information about organic chemistry that you can find in the samples. And first we use it for sorting PET flakes from PVC, plastic flakes, let's say. You have to remove chlorine, the chlorine from the recycling products, or whole bottles like you can see here. This is a fairly easy task, and that was the first application we were involved in. Also interesting is the mining industry, because there are many minerals that cannot be separated using optical systems that are existing on the market, like, let's say, talcum sorting, which is white in color. There's all sorts of other minerals which are not interesting, but they are also white. Using an RGB system it's impossible, but using hyperspectral, near hyperspectral, those minerals can be easily sorted. I said a lot about sorting, so it's not only about sorting. We found out that customers want to know more and more about their product in terms of interesting parameters, like, as I told you, protein content, fat, and they're not actually sorting the product, but they're monitoring the control in order to improve the process parameters in their production. So currently those parameters, like in this image, let's say the moisture, the dry substance in French fries, is monitored by a classical laboratory. Problem with the laboratory is that the people from the laboratory are using quite small sampling quantities from the product stream, like, let's say, 1 kilogram every 20 minutes, to arrive at a heuristics about tons of material, which you can imagine is not very representative. It's slow, it's costly, and it's not representative, so it doesn't sound like a good solution. And it is, in many cases, it isn't a good solution. That's why our technology is pretty disruptive in some production lines, because we're using quantitative chemical imaging, where you are inferring like the moisture content of the product, like you can see here, inline all the time for all the product. This gives you so much data that you can immediately react to any changes in the line. Say you get a delivery, a truck with potato tubers that are not good in quality. With the classical method, maybe it was too late until you realized that you have a problem and that your customer will reject what you will deliver. Because, as I said, a sampling of 20 or 30 minutes at high speeds, that's too slow. With this system, you can, after seconds or at the latest after minutes, by acquiring enough statistical data, control units in your production line further upstream, like a frying unit. You could adjust the temperature of the frying unit in order to reduce the moisture, in order to increase the yield in dry substance. And that's what's done at the moment as we speak. Such systems are sold. They're replacing quality laboratories, or at least adding up to their work to make the product better and to increase the yield. One of the owners of such a factory told me that such a machine brings him 70 euro an hour per line. So you can do the maths back on an envelope and calculate how long it takes that such a machine starts printing money, if you will. So this is a big advantage. Coming to the first real application, we are doing what I just told you in a more general manner in different production sites all over the world. For instance, I'd like to talk about refuse-derived fuels. We had a customer who's got a problem. The problem is that you see here a kiln for in the cement production, and this kiln has to be incinerated with refuse-derived fuels because it's a good alternative to coal, cheap. Problem is, the quality of this material is determined by its origin, and the origin is, you cannot know it. It comes from household waste, and you yourself know what you're chucking away into the waste bin. This can be literally anything: plastic, wood, paper, whatever. Problem is that the important parameters for a fuel, like the calorific value or the moisture you will find in the fuel, cannot be determined a priori. And currently there's no good way to monitor the quality of the fuel, because it could be moist because it had rained on let's say, the dumpster. The calorific value is dependent on the material. You can see on this picture, you cannot say what material it really is. And finding out needs a lab, and the lab, as I told you already, is super slow, it's costly, and the sampling volume they're using is not representative. So actually the same problem like with the French fries. So we use the same technology, quantitative chemical imaging, to characterize the refuse-derived fuel. And you can see on this image, it's very heterogeneous, and this is reflected by the single near-infrared spectra the camera sees. There are several tens of material classes you can define, and so to say software-wise separate before and then assign a calorific or moisture value that you infer from the laboratory and transfer to the camera using special calibration algorithms. So now it's possible to look into the fuel stream all the time and infer a prediction for its calorific value and its moisture, and give this information to some control unit that will arrive at the decision like, okay, the calorific value of this fuel I'm seeing now is too low, so I have to add some more coal to keep the temperature in my kiln, because if the temperature drops, I have to stop the production and have to pay 10,000 of euros. And we convinced ourselves and the customer that the correlation between what the system tells us and his laboratory is good enough to replace it. It's good enough to bring it into the line. So the image I just showed to you looks completely different in the world of quantitative chemical imaging. Some of the parts have a high calorific value, some of them will not give so much energy in the combustion process as others. And by taking a mean value over the whole product stream, you're doing something like a software-wise combustion. You can tell the customer, okay, this fuel will give you this and that many joules in your kiln, and he can work with that. It's like a temperature control, if you like. Another test we did is inline. We applied some extra water, some artificial moistening, and the camera sees that immediately. Here you see, like in the calorific value sample, blue parts are rather dry, whereas red parts are humid. And if you add some extra water, you will see that in the production line immediately, so the camera reacts to that. So all the correlations between the interesting target values like moisture or gross calorific value, which is the value, it's a theoretical value, it's the energy you can get from the fuel if there wouldn't be any humidity, if there wouldn't be any energy taken away from condensation of water. More interesting parameter is the net calorific value. It's the value you will see during combustion. And the correlation factors are good enough to be used inline. So we're going inline, and we are developing further for different locations in the process flow. And some inline data I can show to you is, if you compare our system, which would be the red curve, over time, suffering different systematics from the environment, like different fuel deliveries and other systematics, it shows reduced variance with respect to the laboratory, and that's the actual big advantage. The laboratory will always have local fluctuations which are not representative for the fuel or not interesting, because if you grab like 1 kilogram of fuel out of tons and you're unlucky and you get a piece of wood which has a good calorific value, but the rest of the fuel is of low quality, then this would indicate for a control unit, oh, everything is super, I have a high calorific value, or low moisture in this sense. But it's just not true. So it's better to take all the material and infer a stable mean value. That's what our system is doing. So it's of more help for the production. Same is true for the calorific value, although not as good as with humidity, but also here you see the reduced variance, and the customer is less interested in an absolute correct value. He's more interested in trends. and we can already predict those trends in order to give him the possibility to react to changes in the fuel swiftly. Completely different example from the food industry, but still we use the same technology. So I find it quite amazing that you can use one tool in completely different worlds and it still gives you a solution. In this case, we're talking about chicken breasts. All of you that are eating meat will very likely have eaten a chicken breast in their lives. The industry is facing a problem called wooden breast defect. It's a fibrotic myopathy where the muscle tissue becomes very hard and doesn't look really good. You can see it here, I hope at least. It's of yellowish color, but not really pronounced. And it doesn't just look good. You don't want that on your plate, I'd say. The problem is that optical systems like an RGB camera are not good enough because there are other good fillets that are also of yellow color or can be a little bit harder or whatever, but they're not affected by the wooden breast defect. So it's a defect that can be described by various physical parameters. Others would be calcium content of the muscle and so forth. And one system like RGB can just not do the job. So what is done at the moment is that people, humans, are touching the fillets, looking at them, smelling at them, and after some time reject or accept it. You can imagine that's slow, that's not very efficient, it's costly. So we went into the line and the idea was to infer as many chemometric and physical parameters from the tissue and transfer what we humans can do with our sensory machinery into the camera using artificial intelligence. And that worked out pretty well. If you compare what our system predicts with what a human predicts, we see a clear correlation. It's not perfect, but it's good enough to be installed in the line and to increase the efficiency and ultimately the yield in the production. So we set up such a quantitative chemical imaging model using different parameters like hardness, calcium content, and so forth. And we have so far a happy customer because we can differentiate between affected fillets, shown here, or also here, and good product. In case of the incremented, or in case of the bad product, we see parts in the quantitative chemical imaging stream that go back to hard muscle tissue, but are also affected by increased moisture or, as I said, calcium content. As you can see here, the yellowish pixels would indicate pathological tissue. So, we did mass stream tests with that because it's always one thing if you can show in a proof of principle that something might work, and it's another thing if you go into the production line and bring it to the line. Because you're suffering loads of systematics in the field, and you always have to convince a customer by doing mass stream tests, and we did that, and our accuracy using around about 80 fillets can be computed with 95%, which is for sure a lot better than human beings, which are suffering from operator to operator differences can achieve. So we are ready to go to deploy that into the line, and we hope that the industry will widely accept that. because we are convinced that this will bring a lot of benefit to this industry. And this is another example. I'd like to stress that because I said it in the beginning, but currently we're living in a time where hyperspectral chemical imaging gets known to a broader audience, but there are not enough system integrators, not enough people with expertise out there to use what you can buy on the market, hardware-wise, software-wise. You need still people who know the environment and have the know-how to combine these tools such that you will bring a benefit to the end user. And that's something we identified as a sweet spot for us, and we are earning good money with that. And I can encourage everybody, if he has a problem, to come either to our booth or give us a ring. We are happy to help you. It will take some more years until this technology will become commodity, will end up in our mobile phone, will be used by everybody on the street. At least 5 to 10 years would be my educated guess. Okay, so last but not least, I'd like to say that we are quite happy and proud that for this quantitative chemical imaging tooling, we got this year's Top Innovators Award from Envision. Many thanks to the board that decided for that. And yeah, we are going to use that not only in the food industry and in the chemical industry, it can be also used in mining, and there are various problems out there. And I'm sure people don't know that the technology exists, so I'm here to say, think about it, make up your mind. There is a very interesting and powerful technology that can be used to solve your specific particular quality problem. And that brings me to something like a take-home message. Not only is quantitative chemical imaging rather new, it opens up a very powerful window for applications. In the early years, we talked about sorting, only about information that discerns between good and bad. Now we are talking about information that tells you how bad, how good it is. It brings a degree of quantitative information to the information space, making the applications more sensitive or pinpointing down the solution even better. So solutions or applications that were not possible or you could not solve with existing technology 5 years ago can be solved now using quantitative information that previously only could be inferred by a classical quality laboratory, which always was precise but was slow, costly, and not inline suitable. I'm talking about production lines, fast, dirty, and humid, and it's not a laboratory, it's the production. And I see the possibility to combine the power of a quality laboratory with the statistical power of data inference from a modern smart camera system. So let's say my take-home message is, we are trying to bring the laboratory into your production line. That's the ultimate goal. Okay, that's it. Thanks for bearing with me. And if there are questions, I'm happy to answer.